This is the second recording in the waves unit. It's about specific variables that we will be using to describe what's going on with waves and also calculate each other. There will be one equation that we'll get, the wave equation. So we'll start with the variables. The first one is one that we encountered in the last slideshow. It's the frequency, or F. And again, that is how often one complete wave cycle happens. So it's the cycles per second, otherwise known as a hertz. The second wave variable is one we encountered in the previous units, which is the velocity of the wave. And as I mentioned before, this is how fast an individual wave pulse moves through the material. So sometimes people mix up frequency and velocity. Frequency is like, high frequency means we're jiggling up and down fast, but that doesn't mean the wave is moving sideways fast. So the velocity is how fast the individual wave pulse moves sideways through the material, not how quickly the jiggle is. And velocity is just the same as it has been before. We measure the distance of the medium and how much time it takes for the wave to move and calculate the velocity, which is measured in, the units will be meters per second. The third wave variable, which is a new one, but a pretty straightforward one, is called wavelength. And wavelength is represented by this funny upside down Y symbol that is called a lambda. It's a Greek symbol. And that symbol is basically representing the distance between a crest to another crest or a trough to another trough. In other words, the length of one complete cycle. If you got out a meter stick and held it up next to the material that was jiggling, how far apart would those crests be? What is the length of one complete cycle? And since you could use a meter stick to measure it, the wavelength is measured in meters. So this new variable, this wavelength variable, depends on these other variables. If you look at that picture below, you can obviously see that at the top we've got large wavelength waves. The distance between crests is much bigger. And at the bottom, that purple wave is a small wavelength wave. Those waves have a much smaller distance between consecutive crests or consecutive troughs. So what does that wavelength depend on? Well, if you could picture the person or object making these waves, maybe you can picture them making it in a string, for example. The person at the top is probably moving their arm up and down relatively slowly with a low frequency. And the person at the bottom is probably jiggling up and down quickly. That means they have a high frequency. So one of the variables that the wavelength depends on is the frequency of how often the wave source is jiggling. Long wavelength corresponds with a low frequency of jiggling, and a short wavelength corresponds with a high frequency of jiggling. This means, of course, that wavelength has an indirect relationship with frequency. That isn't the only variable that wavelength depends on, however. And the next one's a little bit trickier to see. But if you look at this diagram of waves in the ocean, it probably will look familiar to you. If you've ever looked at waves way out in the ocean, you notice that there are these big gentle swells and they're pretty far apart. And as those waves get closer and closer to shore, the distance between those waves gets smaller and smaller and smaller. So the wavelength is actually changing as those waves get closer to shore. What's causing this change? Well, as that water gets shallower and shallower and shallower, we're actually changing the medium, okay? Because the depth of that water contributes to how quickly those molecules can bounce back. So when we change the medium, the wavelength changes. The reason why it does this is because the medium, if you'll recall, is responsible for controlling the velocity of the wave. So when waves are moving fast, they have a different wavelength than when waves are moving slow. So the velocity of the wave depends on the medium that it's in, which means that, for a wave that has a set frequency, right, the frequency of the water waves isn't changing, the jiggle isn't changing, the wavelength is going to depend on the velocity of the wave. In the ocean wave example, when the waves are far out in the deep water, they're actually moving fast. Even though they look like a gentle swell, they're actually moving quickly at that time, and that corresponds with a really long wavelength. When those waves get closer to shore, they get slowed down, the medium changes, and there's also a lot of friction with the shore, and that means that we end up having a slower wave, and the wavelength actually decreases. So increasing velocity, increasing wavelength, decreasing velocity, decreasing wavelength. That should inspire you guys to realize that there's another relationship here. Wavelength has a direct relationship with velocity. All right, so if we take the two relationships that we figured out and we combine them, smush them together into a single equation, we start off with wavelength, which is lambda, is equal to, and then take a second and figure out what the equation is going to look like. So remember, there's a direct relationship with velocity and an indirect relationship with frequency, so you should have ended up with wavelength is equal to velocity over frequency. All right, so a quick little check yourself and see if you've understood the stuff that we're doing. I've got two pictures here, two different slinkies. Top slinky is a plastic orange slinky being held by that man, and he's sending a longitudinal wave through the slinky. You'll notice there's a compression right in the middle, and there are rarefactions on the two ends where he's holding. And the picture on the bottom is a more standard metal slinky, and this is a transverse wave, and you can probably pretty clearly see the crests and troughs in that wave. So a couple questions for you. Which of those two waves has a larger wavelength? Please pause it and think. So if you're back, you'll remember that wavelength is the distance between compressions or rarefactions or crests and troughs. At the top, the wavelength is basically going to be the distance between that guy's hands, since there's a rarefaction in each hand. Where on the bottom, the distance is going to be the distance between any two successive crests or troughs. I think that probably the wave on the top has a longer wavelength because his hands look wider than the wave below, but it's pretty close. So the next thing to ask yourself is, which of these two waves is moving faster? Which one of them has a higher velocity? So pause this and think about it for a second. Now, if you recall that velocity is determined by the medium that the wave is moving through, not any other property of the wave, not its frequency or wavelength or amplitude, then hopefully you'll remember that a lighter material has a faster velocity. So since the top slinky is made out of plastic and the bottom slinky is made out of metal, it's likely that the wave at the top is moving much faster than the wave at the bottom. The last question is, which of these two waves has a larger frequency? And I'll let you pause for a second to think about that. And I guess the answer is we probably can't tell for sure, but my instinct tells me that the top one probably has a higher frequency than the bottom one, because their wavelengths are actually pretty similar. There might be a little bit of a difference in wavelength, but they're pretty close. So if we assume that they have about the same wavelength, and I know that the top one has a higher velocity, in order to keep that wavelength the same, we would have to have a much higher frequency as well. So the top one has to have a higher velocity and a higher frequency, because we have a direct relationship with velocity and an indirect relationship with frequency, in order to result in having about the same wavelength as the picture in the bottom. Quick summary of this slideshow. The wave's frequency is determined entirely by how quickly that wave source is jiggling up and down. The wave's velocity is determined only by the medium that the wave is moving through. But the wave's wavelength is determined by both of these. It's related to the frequency in an inverse way and the velocity in a direct way. So we come up with the wave equation to describe what's happening to the wavelength. It's dependent, and the frequency and velocity are independent because they don't affect each other. They just are set by properties of the wave. Thank you.